Hey, welcome back. Before we start, quick question. Have you ever wondered why your computer can run a music app, a browser, and a game all at the same time? Or why you can just download new software and it works, without anyone physically changing anything inside your machine? The answer to both of those questions goes back to one idea. One single idea from 1945 that completely changed computing forever. And once you understand it, you'll never look at a computer the same way again. Today we're talking about the von Neumann architecture. Don't let the name scare you. By the end of this video, you'll understand exactly what it is, why it was revolutionary, and how it still shapes every computer, phone, and tablet you use today. Let's go. First, who was von Neumann? John von Neumann was a mathematician. Born in Hungary in 1903, he was, by almost any measure, one of the most brilliant people who ever lived. We're talking about someone who could memorize entire phone books as a kid, who contributed to quantum mechanics, game theory, economics, and physics, all before turning 40. But the thing he's most remembered for in computer science? He wrote a report in 1945 that described how a computer should be built. And that report became the blueprint for pretty much every computer ever made since then. Now, to understand why his idea was so revolutionary, we need to take a step back and look at what computers were like before him. Imagine it's 1943. World War II is happening. Governments desperately need machines that can calculate things fast, artillery trajectories, ballistic tables, code breaking. So engineers build these enormous machines. We're talking rooms full of wires, vacuum tubes, and switches. The most famous one was called ENIAC. It weighed 30 tons, took up 1,800 square feet, and used so much power that when it turned on, the lights in the surrounding neighborhood dimmed. But here's the thing about ENIAC that most people don't know: it wasn't programmable the way we think of programming today. To make ENIAC do a different task, you literally had to rewire it. By hand. It took teams of engineers days or even weeks to reconfigure the machine for a new calculation. There was no installing new software. You physically changed the hardware. Think about that for a second. It's like if every time you wanted to watch a different YouTube video, you had to open your laptop and rewire the motherboard. Every single time. That was the reality of computing before von Neumann. So what was von Neumann's big idea? Here it is, and it sounds almost too simple. What if the program, the instructions telling the computer what to do, was stored in the same memory as the data? That's it. That's the core insight. Instructions and data, living in the same place, in the same format. This concept is called the stored program computer. And it changed everything. Before this, the program was baked into the hardware, it was physical. After this, the program became just another piece of information. Something you could load, change, swap out, or update without touching a single wire. Here's a way to think about it. Imagine a piano player versus a music box. A music box plays one song. The song is physically punched into a metal cylinder. To play a different song, you need a different cylinder, you need to change the hardware. A piano player can play anything. The piano itself doesn't change. The player reads sheet music, which is just information, stored on paper, and performs whatever is written there. Want a different song? Get different sheet music. The piano stays the same. Von Neumann's insight turned computers from music boxes into pianos. Okay, so now let's get into what this architecture actually looks like. What are the pieces? The von Neumann architecture has 4 main components. They work together like a team, each with a specific job. The first component is the CPU, the central processing unit. This is the brain of the computer. It's where the actual thinking happens, where calculations are done, decisions are made, and instructions are carried out. But here's something important: the CPU itself doesn't store information long term. It just processes it. Think of the CPU like a chef. The chef does all the work, chopping, cooking, plating. But the chef doesn't store the ingredients. The ingredients live somewhere else. Where do they live? In the second component, memory. Memory is where both the program and the data are stored while the computer is running. This is what von Neumann's big idea was all about, putting both in the same place. When you open an app, it gets loaded into memory. When you type something, that text goes into memory. The CPU reads from memory, does its job, and writes results back to memory. If the CPU is the chef, memory is the kitchen counter. Everything the chef needs is laid out there, within arm's reach. The third component is storage. Wait, isn't that the same as memory? No, and this trips a lot of people up. Memory, what we now call RAM, is fast but temporary. When you turn off your computer, everything in RAM disappears. Storage, your hard drive or SSD, is slower but permanent. It's where your files, your operating system, your photos actually live long-term. Going back to the kitchen analogy, if memory is the counter where ingredients are laid out right now, storage is the fridge and pantry. Ingredients sit in the fridge until you need them, then you move them to the counter to work with. The fourth component is input and output, or I/O. Input is how information gets into the computer, keyboard, mouse, microphone, camera. Output is how results come back out, screen, speakers, printer. These four components, CPU, memory, storage, and I/O, connected by pathways called buses, that's the von Neumann architecture. Simple. Elegant. And it works so well that we've been using this exact structure for nearly 80 years. Now let's talk about how the CPU actually uses all of this. Because this is where it gets really satisfying. There's a process the CPU goes through over and over again, billions of times per second. It's called the fetch decode execute cycle. And once you understand it, you'll understand what your processor is actually doing at any given moment. Step 1. Fetch. The CPU goes to memory and picks up the next instruction. What do I need to do next? It grabs that instruction and brings it into itself. Step 2. Decode. The CPU looks at that instruction and figures out what it means. Instructions are written in binary, just zeros and ones, so the CPU has circuitry specifically designed to translate that pattern of zeros and ones into an action. Step 3. Execute. The CPU carries out the instruction. Maybe it adds two numbers together. Maybe it moves data from one place to another. Maybe it checks if a condition is true or false. Whatever the instruction said to do, it does it. Then it immediately starts again. Fetch the next instruction. Decode it. Execute it. Fetch. Decode. Execute. Over and over, billions of times every second. Think about a factory assembly line. A worker picks up a part, looks at the instruction sheet, does the step, then picks up the next part. Except this worker does it 3 billion times a second without taking a single break. That's your CPU. There's one more concept I want to cover, and it's something even a lot of CS students don't fully appreciate, the von Neumann bottleneck. Here's the problem. The CPU and memory are separate. They communicate through a pathway called the bus. And that pathway has a limited width, it can only transfer so much data at a time. The CPU is incredibly fast. Modern CPUs can perform billions of operations per second. But memory? It takes time to read from. And the bus between them? It can only move so much data at once. So you end up with this situation where your CPU is sitting there, twiddling its thumbs, waiting for data to arrive from memory. The CPU is fast. The pipeline feeding it is slow. The processor is starving. This is called the von Neumann bottleneck, and it's one of the fundamental limitations of this architecture. Here's a picture. Imagine a Formula One race car, incredibly fast, powerful, built for speed. But it can only refuel through a garden hose. No matter how fast the car can go, it's limited by how quickly fuel can get to the engine. That's the relationship between the CPU and memory in a von Neumann system. The car is ready. The hose is the bottleneck. So how do modern computers deal with this problem? Engineers have come up with several clever solutions over the decades. The first one is cache. Pronounced cache. Cache is a tiny piece of extremely fast memory that lives right next to, or even inside, the CPU chip itself. It stores copies of the data and instructions that the CPU is using most frequently. Instead of constantly going all the way to RAM, the CPU checks cache first. Most of the time, what it needs is already there. It's like having a small notepad on your desk with your most used information, so you don't have to go to the filing cabinet every single time. Modern CPUs have multiple levels of cache, L1, L2, and L3, each bigger but slightly slower than the last, like layers of proximity to the CPU. The second solution is pipelining. Instead of waiting to finish one fetch decode execute cycle before starting the next, the CPU overlaps them. While one instruction is being executed, the next one is already being decoded, and the one after that is already being fetched. It's like a car wash where multiple cars are at different stages at the same time. You don't wait for the first car to fully exit before the second one enters. The third solution, and this is the big one, is multi-core processors. Instead of one CPU doing everything, modern chips have multiple cores, essentially multiple CPUs on the same chip. Your phone probably has 8 cores. High-end desktops can have 24 or more. Each core can independently fetch, decode, and execute instructions. It's like having multiple chefs in the kitchen instead of one. More work gets done in parallel. None of these solutions eliminate the von Neumann bottleneck entirely, they just manage it better. The fundamental architecture is still there underneath. One more thing worth knowing, not every computer uses von Neumann architecture. There's something called the Harvard architecture, which keeps instruction memory and data memory completely separate, 2 different buses, 2 different memory spaces. This eliminates some bottleneck issues and is commonly used in microcontrollers, tiny chips inside microwaves, washing machines, car dashboards. And more recently, there's been a lot of work on non-von Neumann architectures for AI, because training machine learning models involves moving enormous amounts of data, and the traditional bottleneck becomes a real problem at that scale. But for the vast majority of computing, laptops, desktops, phones, servers, von Neumann is still the foundation. Let's bring it all together. In 1945, John von Neumann described a computer architecture built around one central idea: store both the program and the data in the same memory. This made computers flexible for the first time. Software became something you could change without touching the hardware. That architecture has 4 main components: the CPU, which processes everything; memory, which holds programs and data temporarily; storage, which holds everything permanently; and I/O, which connects the computer to the outside world. The CPU works through a constant cycle: fetch, decode, execute, billions of times per second. The fundamental weakness of this design is the von Neumann bottleneck: the CPU is faster than the pathway feeding it data. Modern computers address this with cache, pipelining, and multiple cores. And despite being nearly 80 years old, this architecture still runs inside virtually every computing device on the planet. Next time, we're going to go one level deeper and look at how the CPU actually works inside: logic gates, ALU, registers. The stuff that turns electricity into thought. If this video helped you understand something that felt confusing before, that's exactly why this channel exists. Subscribe so you don't miss the next one. And drop a comment if there's something you want me to explain. I read every single one. See you in the next one.